Salutations, everyone. Good time zone. Welcome back. I've decided that it's probably a good idea to start out every episode from here on, at least for the foreseeable future, by revisiting our equation sheet. I've already taken the liberty of adding on the new equations, and I have a couple of notes here. One is that for our specific angular momentum here, if you go back to the previous video, you will see that I have r squared theta. That is a no-no. It is r squared theta dot. And the reasoning behind this is, well, the software that I was using to write this didn't let me have the ability to put a dot overhead. So I said, okay, fine, I'll come back to it. And then I forgot. So I'm just going to denote it that way moving forward. Hopefully it's understandable enough. And if not, then I trust that you will let me know, and I'll see about finding a solution around that. The other thing is that I forgot completely about this other parameter equation. And it's a good equation to have on here. So I decided to add it, and this is a good segue for our final closed loop two-body equation, which is going to be yet another angular momentum. So let's go over here and let's get right into that. So we have that our parameter is equal to h squared divided by mu. And it is also equal to our semi-major axis times 1 minus our eccentricity squared. And, solving for the angular momentum here, and I do believe that breaks the record for the fastest that I have ever derived an equation on this series. Go me! So that ought to be the last equation to have for the two-body closed loop, and watch, I'll come back next episode and I'll prove myself wrong. But for now, I think, so I put a little bit of a teaser out last episode about, the escape velocity. Now I think we should actually take a closer look at it. I think we've delayed for long enough. So let's build it up. So a circular orbit, if I put the reference line going out to the right, I do this, then at an angle of theta, our radius will be r. The eccentricity of a circle is 0. So when you plug that into your orbit equation, p over 1 plus e cosine of theta. Well, if e is 0, then that goes away, and the radius becomes p. And the proof of this shall be left as an exercise for the viewer. I think that'll be all right. Our next point of interest is the ellipse, where we have one focus that is occupied and another focus that is not. And as a reference from the orbiting body, if we put in theta and r, we can show that our eccentricity, if I do this right, our eccentricity is between 0 and 1, which means that for our orbit equation, we do p over 1 plus e cosine of theta, then, well, there's not really a whole lot more to cover here because we've already spent an entire episode on this. And I think it's safe to say that we know what to do here. So Now comes the tricky part because I'm not used to drawing parabolas on their sides. So we're going to try doing this. We're going to use our imagination to pretend that it is perfectly done. We draw the reference line out here like that. And again, we put in our theta, we put in our eccentricity of a parabola is equal to 1. Actually, I am not going to draw in, or I'm not going to write in the orbit equation here because we're going to revisit that for hyperbolas. I always tend to think of parabolas as kind of the circles of the trajectories. A hyperbolic description will be just fine for a parabola. So now comes the fun part. You get to see me do some art. So we do that. That's good enough. So we have our orbiting body in here. And you may be asking, what are these lines? And that's a great question. These are tangent lines. Because when we go out to an infinite distance, so say we're coming in from this side, if we want to keep our convention of counterclockwise, we come in from this direction, from a negative infinity, well, from an infinite distance coming in, that's what I'm going to use the minus sign for, it is inbound, then it is not only parallel to that line, it effectively is that line. And then it comes in. I am just hoping my hand doesn't slip. I'm not leaving myself a whole lot of room. That's fine. And then it will go back out. And it will be outbound, so the positive, and it goes out to an infinite distance as well. So, thus the infinity. Something worthy of note here, because this is a hyperbola. It is another conic section. It is, if I had drawn it better, it would have hammered the point home, but it is symmetric. So on the other side of this X right here, there is another empty focus and a conjugate hyperbola. We're not going to be dealing with that too much because while it makes sense geometrically, physically, it doesn't make as much sense. So we're just going to focus on the actual trajectory hyperbola. And I'm going to, let's see, we'll do that. R and theta. And as one might suggest, our eccentricity is greater than 1. I said as one might suggest. As one might expect, our eccentricity is greater than 1. So again, if we were to look at our orbit equation, we see that there is a problem. Because at some point, this denominator goes to 0. And that kind of causes a few problems, mathematically speaking. We don't like zeros in denominators. But there's a way around this. So if we were to extract our denominator, and we find out, okay, at what point does it become 0? Said another way, at what angle does the body, does our orbiting body leave our host body? And if we were to solve for this, then you would see that at the arc cosine of -1 over the eccentricity, we effectively lose contact with our satellite. And if we were to put a label onto it, so we are using a convention of positive is anti-clockwise from the reference. So when you put this together, you are actually defining that angle where it is the angle of the escape, not the inbound, but the escape. And that is one of those important equations that we've been trying to find. There's more to it than that, though, because as it turns out, this is oh so pretty in that it is symmetric in many different ways. So if this is our escape trajectory, because it is symmetric, it's conserved. We can see that that is also the angle of our approach, or our inbound angle, I guess is the phrasing I'll use for that. That is our inbound angle. And it is negative from the outbound angle. It is just on the other, it's just reflected. Now, to put that another way, that angle is 180 degrees minus the inbound angle, right? So if we were to flip everything around and we were to go from this direction, that is the same as that. I'm not going to leave that up there because that's going to make it a mess. And also, I'm just going to draw right over it. These are useful for determining something called a turning angle, where we can see that, okay, we had been going in this direction, but now we are going in this direction. What is the angle that we are turning? Which is where it gets its name. Fun fact. So to write this down, we see that our turning angle is equal to our outbound angle minus the minus 180 degrees minus our inbound angle. And so distributing the minus sign here and rewriting, we can actually see that this is going to be 2 times the outbound angle minus 180 degrees. We know what our outbound angle is, so let's put in that equation. Let's plug that in. All right. And so we get here. And this is perfectly valid, but this is not the most reduced that this can get. For that, if we play around with the maths here, and if I were to negate this equation, okay, so we have minus cosine, we have 1 over e is equal to minus cosine delta by 2 plus 90 degrees. Cosine plus 90 degrees. That screams to me that there is a phase shift in here. So if we were to make ourselves a minus cosine graph, we would get something that looks not like that. Not like that. because cosine starts at 1, it is negated, it starts down here. Not perfect, but good enough. Phase shifting it positive 90 degrees will get us something that looks like this. Again, not perfect, but you understand what I'm going for. Where this is our minus cosine, and this is our minus sine. So to write this another way, we have 1 over e equal to the sine of delta by 2. And if we were to solve explicitly for the delta here, then we would get something that looks like this. Delta is equal to 2 times the arc sine of 1 over e. Sorry about the pauses. A cat just jumped into my lap. Yes, I do have a cat. At least one. Now that you know that about me, and now that I have written up the equation, let's box this equation. Because that is the equation for the turning angle. And ordinarily, I would write up an example to play around with this to give us proofs of concept. But I think this video is going long enough, and we need a little bit more information before we can comfortably do that. So, welcome to the first ever 2-part episode on this channel. I will have something out for you guys next week. Until then, thank you so much for stopping by.